Hi everybody, welcome to another edition of Fast Science Concepts. This builds on from the first one to do with active and passive transport, and what I'm going to do today is delve a little bit into the world of osmosis. This will include a practical, which you have to do, it's a required practical, and I want to just talk over the fundamental ideas that help you understand this process of osmosis. I've drawn a few things on my front cover here. Hopefully you'll be able to spot these things as we move through. A lot of our knowledge of osmosis and the context we explain them in as teachers are to do with plant tissues. I'll say now that osmosis can happen in any tissue, in any cell, animal or plant. However, we do tend to focus on the importance of osmosis in plants. So here we go. Fundamental to your understanding of what osmosis is, and indeed diffusion as a whole, is knowing what concentration is. You're going to have to excuse my poor artistic skills here. I've drawn these two cups slightly different sizes. I'm not an art teacher. I'm a science teacher, so I thought I'd explain that and make excuses before I went on and did any further kind of explanation. However, I would like you to imagine that these two cups are the same size. One of the things that I really love to do when I get home is make myself a nice glass of Ribena. It's the drink of champions. If I make a glass of Ribena and I put this much Ribena in and fill it up, I'll have a nice glass of Ribena. If I put this much Ribena in and fill the rest up with water, I will have an entirely different drink. So the question I want you to ask yourself now while you look at these, which one is the strongest solution of Ribena? Which is the most concentrated solution of Ribena? We need to think about a working definition of concentration. And the way I want you to think about this is that it's the amount of particles in a certain volume. Okay, so that's how you need to think about it. So if we compare our two glasses again, this will definitely be the most concentrated Ribena because it's got the most concentrated. I've poured the most liquid of Ribena in there. Okay, this will be the least concentrated. Solution for Ribena because there's less in there. All right. Most of this glass will be water. The rest of it will be the Ribena. Here, there'll be less water than Ribena. So you're having a more concentrated solution over you've put more Ribena in. Now, when we start talking about osmosis, we're talking about the diffusion of water from a high concentration of water to a low concentration of water. So if we go back to our glasses, in which glass do we have the most concentrated solution of water? It's the opposite. We have a more concentrated water solution here. Okay. And we have a least concentrated water here. Now, essentially, this is quite a difficult thing to think about. essentially we don't ever really think of water as having concentration. And when we're talking about osmosis, we are specifically talking about the movement of water and the concentration of water. A way to think about this is that if you have a pure glass of water with nothing else in it and you pour Ribena in it, you are diluting that water with the Ribena, not the other way around, if we're just thinking about water. This is tricky conceptually because we, as I said, we don't have this sort of thought in our head of water as having an inherent concentration. We use it to dilute other things like acids, other things in chemistry, other solutions in chemistry. Okay, we use water to dilute things, so we don't think about it as having its own concentration, but it does. And we can think about that concentration as relative to whatever we dissolve in it. So let's quickly recap. Concentration is the amount of particles in a certain volume. When you add or dissolve more things in water, like Ribena or salt or sucrose, you decrease the water's concentration. So we need to have that in the forefront of our mind when we start talking about osmosis, especially when we start looking at the required practical. Okay, so let's move on. Let's quickly recap on what osmosis is. Okay, remember, osmosis is passive transport. That means it requires no additional energy from the cell. There's energy involved. The particles have kinetic energy. They're moving randomly around. This is a very static diagram, but actually those particles would be moving. And they move across this hatched line here, which I've put in to represent the cell membrane. Now, this is important to think about. We're looking at just the diffusion of water. Okay, so this is water. This is at a high concentration. And this is at a low concentration. And it's across the cell membrane. We call this a concentration gradient. And high to low is with the concentration gradient. The reason it's passive transport, this will just happen on its own until those concentrations are equal on both sides of the membrane. The particles won't stop moving, but there'll be no net movement in any particular direction. The cell does not have to put any energy in to get this to happen. It happens because of the kinetic energy that the particles have anyway, and that's why we call it passive transport. So this is something to remember. Okay, let's put a few keywords down about this. Okay, it's passive. It's a net movement of particles from high to low concentration. And it can happen with animal and plant cells. It doesn't just happen in plant tissues, it can happen in both types of tissue, in both types of cell. Okay, so that's just a little recap on what passive transport is and how it relates to osmosis. The other important thing I need to put in here, osmosis is just the diffusion of water. Right, so one of the required practicals you have to do at GCSE is finding the concentration of a potato cell cytoplasm. Okay, now you can do an experiment using osmosis to ascertain the concentration of potato cell cytoplasm. Right, now what you'll do is you'll get 1, 2, 3, 4, 5. Okay, so you'll get 5 test tubes. And you'll fill them full of a salt solution. Okay, and these will be the concentrations you'll use generally. Okay, so you get 5 of these. And in them you'll place, let's draw it here, a little core of potato. Okay, so what you'll do once you've done that is you'll set it up. Way before, dry, way after, dry, and you'll work out the percentage change in mass. Okay, you're going to have to leave it for a little while. So generally a day or so between weighing them. Okay, so you'll have 5 test tubes. Each test tube will have one of these in, one of these concentrations of salt solution, and you weigh them before you put them in, you weigh them when they come out, and you'll use that to work out the percentage change in mass. Okay, let's go back to these concentrations. Thinking back to what I said about the Ribena bottle, the Ribena drink that we've made. Looking at these salt concentrations, this is just table salt, sodium chloride. Which end is the most concentrated salt? Let's use a different colour for this. Okay, okay. So at this end we've got 1 mole of salt solution. So this is the most concentrated salt. And at this end you have the most concentrated water. So let's think about this. It makes sense, okay? So this is pure water, so it's the most concentrated water. When I say pure, it's not got anything additional dissolved in it. As you're dissolving more and more salt in the water and you're getting more concentrated solutions of salt, the concentration of the water goes down, all right? So this will be the least concentrated water. And at this end, this will be the least concentrated salt. So knowing what we know about osmosis, it's the movement of water from a high concentration of water to a low concentration of water, you would expect to see at this end water entering the chip and it weighing more after the experiment. Its mass should go up over here, okay? As you get a more concentrated salt solution, you'd expect water to leave the chip. The concentration of the cytoplasm inside of water would be greater inside than outside, so water would leave high concentration to low concentration. So you'd expect the chips at this end, the cores at this end, to lose mass through osmosis. So what does that look like? What you'll end up with is a set of percentage changes, okay? At this point, I just want to focus on a few things I've said, all right? So in terms of dry mass, we always look at the dry mass. We'll dab it with some blue roll because we need to remove excess water. Remember, we only want to know what the dry weight of that potato core is. We don't want the excess water changing that result. The reason we use a percentage means that we don't need to worry, no worries, about start and end mass being accurate. Okay, you don't really have to be that accurate with it. What you're looking at is you're looking at the percentage change of each chip. It becomes a proportional change as opposed to an exact change in mass. If we think about it for a minute, if we were setting up this experiment and we weren't going to work out percentage change, all of these start masses of our potato chip would have to be the same, which is really hard to do, especially in a school lab, as we all know. Not enough scalpels to go round, distraction. So it's very hard to do that. Inaccurate scales, all sorts of things can come into play. So by changing this, our end result into a percentage change, we're able to kind of mitigate those inaccuracies. All right. So this is what you'll do. Once you've got that data, you'll plot yourself a graph, and it is a wonderful graph. It's sad that I get so excited about these things, but I am a science teacher, and there you go. I'm not going to say any more about that. Graphs excite me. So this is what our graph would look like, okay? On the y-axis, you'll have percentage change in mass. If a chip has gained weight, you'll say it's got a positive change in mass. If it's lost weight, you'll say it's negative. And you'll simply plot it. Here are your concentrations. So let's do a nice purple line. Let's say in the 0 salt solution, it put on quite a lot of mass. Your graph should look something a little bit like that. Okay, so on this side, with these concentrations, water has entered the cell because the mass has gone up. On this side, with these more concentrated salt solutions, water has left the cell and it has lost mass. Okay. Now, if we want to find the exact concentration of that cytoplasm, we look at this point here. Because if you look at this point here, our potato chip has neither gained or lost any mass. Right, so that's the point where the concentrations on both sides will be equal. So that will be the concentration of our chip. So let's recap on that. So here, water has entered the chip. So there's an increase in mass. Here, water has left the potato. And this caused a decrease in mass. This point here, equal concentrations, equals no loss in mass. Equals no net movement or gain in mass, equals the concentration of the cell. Okay, so the take home here, make sure you know how the concentration, the relative concentration of water changes as you add solute to it. Bear in mind when we talk about the movement of water, the direction of osmosis, we need to be sure about where the most concentrated solution of water is. When you interpret this graph, wherever it crosses the x-axis is your the concentration of your cell. And remember, what's happening here is there is no sort of net movement in any particular direction. So there's no loss in mass or no gain in mass. So this is where you'd find the concentration of your potato chip. Okay, so that's osmosis. That's everything you need to know for GCSE. Please like and subscribe. I'll do another one of these next week and we'll see how we go. Okay, thanks a lot. Have a good weekend.